Hi all, welcome to Discrete Mathematics Tutorial 10. In this tutorial we are covering two topics, which is binomial theorem and the pigeonhole principle. Now before we begin, I'll just explain what binomial theorem is. So according to the theorem, it is possible to expand the polynomial x plus y to the power n into a sum involving terms of the form a constant a multiplied by x to power b y to power c, where these exponents b and c are some non-negative integers and b plus c is equal to n, and the coefficient a is of each term in the expansion is a specific positive integer, and it depends upon n and these coefficients b and c. So let's just write down the expansion. X plus y to the power n is equal to nc0 x to power n y to power 0. So this n0 is the combinatorics. So, and the next term would be nc1 x to power n minus 1 y to power 1 plus nc2 x to power n minus 2 y to power 2. And this goes on till nc(n minus 1 x to power 1 y to power n minus 1 plus ncn x to power 0 y to power n. Now one thing to note here is that the first term's coefficient will be equal to the coefficient of the last term. That means nc0 is equal to ncn. So to generalize it, it is ncr is equal to ncn minus r. And the formula for a combination is ncr is equal to n factorial over r factorial times n minus r factorial. Now, there's a generalized definition of the binomial formula, which looks like x plus y to the power n is equal to summation from k equals 0 till n nck x to power n minus k y to power k. So now we have these basic formulas ready. We can go on to the questions. Now the first question was determine the coefficient of x to power 9 y to power 3 in the expansion of x plus y to the power 12. So using the formula in this rectangle, we have n as 12 and our k would be the coefficient of the power of y, which is 3. So just plugging it into the formula, it is 12c3 x to power 12 minus 3, which is equal to 9 y to power 3. Now 12c3 would be the coefficient, so calculating that, 12c3 is equal to 12 factorial over 3 factorial times 9 factorial. Solving it, it's equal to 220, which is the coefficient of x to power 9 y to power 3 in the above polynomial. Now the second part, it is x plus 2y to the power 12. Again, we have to find the coefficient of x to power 9, y to power 3. Here again, n would be equal to 12 and k is 3. And we already know what 12c3 is equal to. Now the only difference between this and the above problem is y has a 2 attached to it. So the expansion would be 12c3 x to power 9 2y to the power 3. All we need to do is multiply 220 by 2 to power 3, which is 8. And that will give us the coefficient, which is 1760. So if you are confused about problems like this, you can just substitute 2y as another variable, b or c, and just solve it in a normal way. The third problem here, it is 2x minus 3y to the power 12. Now, just to simplify this, we'll assume a as 2x and b as 3y. So a is 2x, b is minus 3y. This gives us the standard polynomial, which is a plus b to the power 12. Now again, our n is 12, k is 3, and we know that 12c3 is 220. So adding it in the formula, 12c3, a to power 9, b to power 3, it's 220. Now substituting a and b back again, 2x to the power 9 minus 3y to the power 3. This gives us 220 multiplied by 2 to the power 9 is 512, and minus 3 to the power 3 is negative 27. So the coefficient comes out to be minus 3,041,280. Now moving on to the next question. It is x minus y to the power 14. Now, since we wanted to find the coefficient of x to power 9, y to power 3, 9 plus 3 is 12, which is not equal to 14. Therefore, this term is not present in the expansion of the above polynomial. Always the powers of x and y, when you add them, they should be equal to n, which is the power of the polynomial. Now, the second question, it says determine x if summation I from 0 to 50, 50 ci, 8 to power I is equal to x to power 100. Now, from the binomial theorem, we had this definition x plus y to the power n is equal to summation k equals 0 to n nck x to power n minus k y to power k. Now another variant of the binomial formula can be obtained by substituting y as 1 so that it involves only a single variable. And we can see that in the question itself, we just had 8 to power I. So we wanted the equation in a single variable. Now the formula reads 1 plus x to power n is equal to summation k from 0 to n nck x to power k. Now one thing to note here is that in above we had x to power n minus k. Now I've written x to power k. The reason is that the coefficient of x to power k is equal to coefficient of x to power n minus k, and we've established that earlier. This can also be verified through Pascal's triangle or just by solving the formula for combinations. Now, putting back the original question here, so summation I equals 0 to 50, 50 Ci into 8 to power I. This is equal to 1 plus, now here our x is 8, so it would be 1 plus 8 to the power 50. And our right-hand side of the question was x to power 100. So 9 to power 50 is equal to x to power 100. This can be written as x squared to the power 50. Therefore, x squared is equal to 9 and x is equal to plus minus 3. And that's our solution for this question. Moving on to the next. Show that for all positive integers m and n times m plus n c m is equal to m plus 1 times m plus n c m plus 1. We'll start by solving the left hand side, which is n times m plus n cm. The formula for combinations is n factorial over r factorial into n minus r factorial. So using that, we get n times m plus n factorial over m factorial n factorial. Now, just to see what we need to solve up to, I'll just simplify the right hand side and see what it looks like. Use the formula for combinations here. This would give me m plus 1 times m plus n factorial over m plus 1 factorial multiplied by m plus n minus m plus 1, which is n minus 1 factorial. Now, coming back to the left-hand side, we'll solve it further. In the denominator, n factorial can be rewritten as n times n minus 1 factorial. Now, these n's cancel out, which leaves us with m plus n factorial over m factorial n minus 1 factorial. Now we can multiply the numerator and denominator by the same number, which would be m plus 1. And this gives us m plus 1 times m plus n factorial over m plus 1 into m factorial into n minus 1 factorial. So m plus 1 times m factorial is m plus 1 factorial, which is, if you multiply 3 into 2 factorial, it's equal to 3 factorial. So with this, our left hand side is equal to the right hand side, hence proved. Now this question is quite simple. With n a positive integer, we have to evaluate the sum nc0 minus 3 times nc1 plus 3 square nc2 minus 3 cube nc3, so on till minus 1 to the power n, 3 to the power n, ncn. Now you can see the number 3 is just increasing in power, but it's the sign that's alternating. So we'll just see what from the basic formula of the binomial theorem, 1 plus x to power n. Now If we say x is equal to minus 3, this just looks like our problem. Uh, so minus 1 minus 3 to power n is equal to summation from 0 to n nck minus 3 to power k. Now here you can see if you say k equals 0, the first term comes up, nc0. For k equals 1, it is nc1 times minus 3, which is exactly our first term. So this way we can write down all our terms. But on the left hand side, that is what our summation basically is, which is minus 2 to the power n. And that's our solution. Now, for this problem, we have to show nc0 plus nc2 plus nc4, so on, is equal to nc1 plus nc3 plus nc5. Now again, the expansion of, let's start with the expansion of 1 plus x to power n, which is summation k from 0 to n, nck x to power k. Now expanding it gives us nc0 x to power 0, which is 1, plus nc1 x to power 1, plus nc2 x to power 2, plus nc3 x to power 3, so on. Now for x equals minus 1, our left hand side would become 0 to power n, and the right hand side here now is nc0 minus nc1 plus nc2 minus nc3, because the even powers would negate the negative sign while the odd powers will keep that sign. So we'll just separate out the negative terms. Now, one side we have nc0 plus nc2 plus nc4, so on, minus we'll have nc1 plus nc3 plus nc5 and so on. Now rearranging this equation, taking the negative terms on the other side, we get nc0 plus nc2 plus nc4 is equal to nc1 plus nc3 plus nc5 and so on, which is exactly what we were asked. Now you could even go a step further and see what they are actually equal to. To solve that, you'll have to substitute x equals 1 and compute this, which will give you that the above equations or the above summations are equal to 2 to the power n minus 1. For the sixth question we have, show that if any 14 numbers are selected from the set S, which is 1, 2, 3 till 25, there are at least 2 whose sum is 26. Now this is a typical problem of pigeonhole principle, the definition of which is pigeonhole principle states that if n items or n pigeons are put into m containers or m pigeonholes, where we know that n is greater than m. So this is one important thing to look at. N has to be greater than m. Then at least one container must contain more than one item. So if you have 3 balls and 2 boxes, when you put one ball in each box, you'll have a box which contains more than one balls. For this question, let the pigeons be the numbers which are to be selected, and now we define the pigeonholes corresponding to the 13 sets. These sets would be the numbers which, when added, they sum up to 26. So this set would be 1 comma 25, the other set is 2 comma 24, 3 comma 23, 4 22, 5 and 21, 6 and 20, 7 comma 19, 8 and 18, 9 17, 10 16, 11 15, 12 14, and 13. Now here, one thing to note is that the numbers in each of the first 12 sets sum up to 26, and there is no pair of distinct numbers containing 13 that sum to 26. So when a number is selected, it gets placed into the pigeonhole corresponding to the set that contains it. So let's say you select 1, you'll put it in the first set. When you select 13, you put it in the last set. Now, we all know that we have 13 sets available, but we are to select 14 numbers. So when you select 14 numbers and place them in 13 pigeonholes, some pigeonholes would contain more than 2 numbers. Therefore, you will have at least 2 numbers whose sum will be equal to 26. For the 7th question, we have, during the first 6 weeks of his senior year in college, Brace sends out at least 1 resume each day, but no more than 60 resumes in total. Show that there is a period of consecutive days during which he sends out exactly 23 resumes. So 6 weeks is 42 days. Now, so he sends out 1 resume, at least 1 resume each day for 42 days. And in total, he sends out less than 60 resumes. So to write it formally, it is for I between 1 to 42, let x of I be the total number of resumes Brace sent out from the start of his senior year to the ith day. Now this is 1 is less than equal to x1, which is less than x2, less than x3, so on till 42, which is less than or equal to 60. So x2 means x1 plus the letters he sent out on the second day, and x3 would mean letters he sent out till second day plus the third day. Now, once we have this inequality, we can add 23 across the whole inequality, which gives 1 plus 23 less than equal to x1 plus 23 less than x2 plus 23, so on till x4 42 plus 23, which is less than or equal to 83. Now we have 40, in total we have 84 distinct numbers. So 42 distinct numbers are x1, x2, so on till x42, and another 42 distinct numbers which are x1 plus x23, x2 plus 23, x3 plus 23, so on till x42 plus 23. And they are all between 1 and 83 inclusive, which means the number 1 and 83 is included in these numbers. So in total, we have 84 elements, which could be x1, x2, x42, or x1 plus 23, x2 plus 23, anything. So we have for 84 elements to choose between 1 and 83. So there's one extra element to choose in within these numbers. So by pigeonhole principle, at least two of them must be equal. So there is a period of consecutive days from J to I where he sent out exactly 23 resumes. Xi is equal to xj plus 23 and j is less than I. So the difference between xi and xj is exactly 23. Moving on to the last problem, it says let xi, yi, where I is 1, 2, 3, 4, 5, be a set of 5 distinct points with integer coordinates in the xy plane. Now we have to show that the midpoint of the line joining at least one pair of these points has integer coordinates. Now let's take 2 points whose coordinates are AB and CD. The midpoints of the segments whose endpoints will be AB and CD would be A plus C by 2 and B plus D by 2. These are the coordinates of the midpoint. Now, since we are concerned only with the integer values of the original coordinates, which are A, B, C, D, these fractions, which is the midpoint, the fractions will be integer only and only if A and C have the same polarity, which is either they are both even or they are both odd, and the same goes for B and D as well, because we know even plus even is even, odd plus odd is even as well. So we need them to have the same polarity so that when divided by 2 they gives us integers. Now there are 4 possible pairs of parities possible. which would be odd and odd, odd and even. The third one is even and odd, and the fourth one is even and even. Now, since we are given 5 points, the pigeonhole principle guarantees that at least two of them will have the same pair of parities. So if you take your first point to be odd odd, second point to be odd even, third point to be even odd, the fourth point to be even even, the fifth point will have to be repeated from either of these. So the midpoint of the segment joining these 2 points, which had the same parity, will have integer coordinates. So this concludes the tutorial for today. See you guys next week.